Hi everyone, in this video we'll work through an example about friction. Let's get right to it. This one says, a group of students attach a massless string to a 165 wooden block and place it on a surface. The string goes through a modified Atwood machine, that is a frictionless pulley, and a hanging mass 85 grams is attached to the other end of the string. Find the coefficient of friction. Assume 85 grams is the maximum hanging mass which can be attached so that the block does not move. So a modified Atwood machine is just like one pulley here. So this is the pulley over here. We have the 165 wooden block attached to a massless string. I know massless, but that's the way we do it in physics, at least at this level. And we have a hanging mass. It's hanging, thus hanging mass here, right? In this case, we have no movement, no motion. Our system does not move. And friction is present, right? Because we have to find the coefficient of friction. Therefore, we know friction is present. In this case, friction will only be affecting the wooden block, not the hanging mass, because the wooden block is on the surface. Okay. The first thing we want to do is write down the given information. I want to highlight, right? So we have a 165 wooden block, and then we have, well, the string is massless, the pulley is frictionless, so we don't have to worry about that. And then we have a 165, an 85 gram mass is attached to the other end of the string. That is also very important. And our main goal, our task, is to find the coefficient of friction. Okay. And the last sentence is very, very important. And I'll explain why in just a moment. Let's write down our given information. Given. So we have, let's call this mass 1, M1, and I'm going to call this one mass 2. So mass 1 is equal to 165 grams. Mass 2 is equal to 85 grams. And that's all we know. Well, we know that both masses are being affected by the force of gravity, right? By their weight. And to find weight, we have to use acceleration of gravity, and we know that is 9.8 meters per second squared. And we have to find the coefficient of friction, which is the Greek letter mu. Now, in this case, we have to decide, or not decide, but we have to figure out if we're going to find static friction, so we can find the coefficient of static friction, or kinetic friction, the coefficient of kinetic friction. And the key is the very last sentence. Assume 85 grams is the max so that the block does not move. If it is not moving, if it's at rest, motionless, then that means we have to find static friction. We're going to be using static friction. That is very, very important. So we have to find mu subscript s, coefficient of static friction, question mark. Okay. We don't have a lot of information, but we know this is a problem about forces. This is an example about forces. Therefore, we should draw free body diagrams. We have to draw a free body diagram per object in this problem. So we'll draw a free body diagram for mass 1 and then a free body diagram for mass 2 because we're going to treat them as independent from each other. Though we know they're connected by a string, we're going to treat them as independent from each other. Okay? So let's start with our free body diagram, our FBD. Free body diagram. And the block, I'll draw them the same way. So start with the block. Well, I'm going to say mass 1. Block, which is M1. So we have something like this, more or less. Yeah. There you go. And let's see what forces are acting on this block. Well, let's find the center of mass. There you go. We know we have the force of gravity, or the weight of the object, which is pointing straight down. Let's label. This will be mg. Well, m1g, right? Because mass 1. There you go. And then we have a force equal and opposite, because this is not moving up nor down. So let me make sure my arrow has the same magnitude, but opposite direction. There you go. And due to the fact that the block is on a surface, well, that means the force against weight is normal force. Weird end. Weird end. Okay? I know some of you like to write F sub n, and that's fine. But most problems, like in Quest or your exam, will have that weird n. So that's why I want to use it, so you can get used to that weird n. But that's, if you use F sub n for force normal, that's fine. Okay? That's fine. Now, in the horizontal direction, well, we have a string which is pulling on the mass, though it's not moving. We know it's pulling because there's tension, right? It's pulling on it. So we have tension to the right. There you go. Tension is away from the center of mass. And we use capital T for tension. And friction is acting against tension, right? Because tension wants to pull the block to the right. Due to the fact that this is not moving, it means that friction is pushing or is acting on the opposite direction, which is to the left. So tension wants to pull the block to the right, but tension is resisting, right? It's acting against, which means the force is towards the left. So again, they have to be equal and opposite. We have no motion. Got to make sure they have the same magnitude. Uh-oh. And we'll move this one over here. And we said we have static friction. Now, normally we write force of friction like this, right? F sub F. But since we have so many forces, so many F's, I'm going to use just lowercase f for friction, for force of friction, and then add an S, a subscript S for. This is force of static friction, friction static. Okay, that is our free body diagram for block or mass 1. And now I'm going to draw a free body diagram for the hanging mass, which is M2. M2. Okay, I'm going to try to copy the shape. There you go. Well, let's make sure it looks almost identical as much as I can. It's not gonna work. That's fine. That's fine. It doesn't matter. Okay? It doesn't have to be perfect. So there's our hanging mass. We know that. Oh, let's find the center of mass. There you go. And we only have two forces acting on this thing, right? Because it's just hanging. It's attached to a string. You got the weight down and the string and the tension up. So we have the weight down. There you go. Let's label that force. This is weight, or M2G. mass 2 times acceleration due to gravity. That is the weight of mass 2. This is not moving, therefore there should be a force equal and opposite. This is not resting on a surface, which means we have just the tension force, which is holding this mass in place, and this tension T. Before we continue, one thing I want to point out is that since we have the same strain and it's massless, we can consider the two tensions being the same. So tension here is going to be the same tension here. So these two tensions are the same. These two forces are the same. That's why I didn't write tension 1 or tension 2, because it's the same. And that's very convenient. Another thing I want to point out is that signs are very important. Since we have two objects, we could have our frame of reference is going to change based on the motion. So when we have two objects and pulleys, it is very important that even though this situation has a mass which is not moving, excuse me, which is not moving, we have to ask ourselves, what if it's moving, right? What if we place more than 85 grams here? Well, if we place more than 85 grams, then this mass 2 will pull effectively, and then this mass will start moving to the right. Mass 1 will move to the right because the pull, right, because the weight of mass 2 is going to increase, which is going to increase tension, which is going to increase tension over here on this side. And we're going to beat static friction, and now we're going to have kinetic friction. But the main thing is, okay, if this were moving, what is the natural direction of motion? Well, if we apply more mass, this moves down and this moves to the right. So the natural direction of motion becomes the positive direction, okay? The natural direction of motion becomes the positive direction. Let me write it down. That way we don't forget. The natural direction of motion becomes the positive direction. Now, you could make it negative, of course, but I think it's that this way is easier. I like this way better, okay? Again, if you want to make the natural direction of motion negative, by all means, but I like to make it positive. Which means, well, the block, mass 1, will move to the right. So forces moving to the right are positive. In this case, tension, this tension, right, this one over here, just this one, is positive. So I'm going to add a plus sign. Well, in this case, the block M1 is not moving up or down, so we'll just use the conventional down is negative, up is positive. So normal is positive, M1G is negative. If tension to the right is positive, then force of friction is negative because that is to the left. You'll see why this is very, very important, guys. You'll see, okay? Now let's move to block number 2, well, to the hanging mass. So the hanging mass would move down. That's the natural direction, right? Moving down. That means M2G is positive, which means tension is negative because tension would be against the natural motion because the natural motion is down. So minus. In fact, let me draw a supposition, right? If this were moving, it would move like that. The pulley would rotate clockwise and it would move like that. Let me try to draw that arrow, right? It will move like that. Okay, that would be the natural direction of motion if this were moving, but it isn't. Okay, now that we have our free body diagrams, we added positive and negative directions. Then the next step is to sum the forces, that is, add the forces acting on both x and y direction because we treat them independently, just like we did in projectile motion. So next step, we're going to sum the forces. Sum the forces. Let me try to use that nice purple that I used last time. So next, we sum the forces. Sum is adding, okay? Sum is adding. Oh, sum forces. Okay, let's start with M1. Don't forget we use the Greek letter sigma, that is summation of the forces acting. Let's start with the y. Along the y direction for mass 1, that's what it means. This is summation of forces along the y for mass 1. Okay? Is it equal to? Well, along the y we have, is the vertical, right? We have normal, which is positive, weight, which is negative. So it would be normal minus m1g. And this is equal to 0 because the system is not moving, it's not accelerating, right? It's not accelerating. And there we go, that's it. We only have two forces acting along the y. Now let's do the same thing for the x. The summation of forces along the x for mass 1 is, well, in this case we have tension, which is positive to the right, and force of friction, static, which is negative to the left. So it'd be tension minus force of static friction is equal to 0. Because it's not moving to the left or right. The block does not move. There you go. Next, we'll sum the forces for mass 2. And this one's easier. We only have the y direction. X is, there's no forces, so we only have to do the y. So the summation of forces for y, mass 2, is equal to, now be very careful. And for mass 1, tension was positive. For mass 2, tension is negative. The weight is positive. So we'll have m2g. Let's try that 2 again. m2g minus t is equal to 0 because this is just suspended in the air. Right? It's just hanging. It's not moving. Okay. So now what do we do? Well, let's not forget we have to find the coefficient of static friction. But this is not even here, right? Well, let me remind you that the equation or formula for friction, so equation for friction, let me change color. That way, let me use red and then I'll box it. So the equation for friction goes like this. Friction is equal to the coefficient of static friction, coefficient of friction, just times the normal force. Okay? Let me label this. F is force of friction mu is the coefficient of static friction. Oh man, I keep saying static. Just coefficient of friction. Coefficient of friction. And then that weird end, don't forget, oh man, that came out way too weird. That weird end is normal force. Okay. So now, you know what, let me move this elsewhere. I don't like it here. I'm gonna move it maybe over here. No, it's too crammed. I guess here, on this side. Okay, so you don't forget. So now what I'm going to do is I'm going to substitute this equation here, with the exception that we have static friction, and all we do is we add the subscript s here for coefficient of static friction, right? Because this is just coefficient of friction. We're not saying if it's static or kinetic. to state that it's static, we add the little s here because we would add it on F sub s like we have over here. So that means the summation of forces along the x for mass 1 is tension minus coefficient of static friction times the normal force. That's equal to 0. Okay. So now what we have to do is, what is the force which is making the system to be static or not moving? Would be friction, right? Friction is what's holding mass 1. It's not letting it move, because weight and normal force are perfectly balanced, and the force which is balancing tension, because tension's pulling, would be friction. Okay, so this is the equation that we're gonna have to be working with over here, this one over here. Since these two equal 0, if I only take this part, right, if I only take this part over here, just this part, and say, okay, tension minus mu s normal force is equal to 0. To know what the force of friction is, so I just add this to both sides, right? So I would add this to both sides. So I move mu sub s n to the right. I move the force of friction to the right. This cancels, and I have that tension is equal to the friction force, mu sub s times n. Because this is what I'm looking for, mu sub s, right? Yeah, mu sub s over here. There's a problem. I don't know what the normal force is. I don't know what it is. What I can do is get this equation over here for the y, because since these two are equal to 0 when subtracted, that means they're equal and opposite. Think about it. This is not moving down nor up. That means these two forces are equal and opposite. So I would do the same steps, right? I'm not gonna do that, but I'm just gonna move m1g to the right, and that will give me normal force. Normal force. Let's try that again. Normal force is equal to m1g. So now I will combine those two. Okay, I will combine those two. So I'm going to substitute m1g here. Okay, I use a different color now. Tension is equal to mu sub s times m1g. Okay, because we do have m1 is 165 grams. We know what g is, and we're trying to find mu sub s. Now we have to deal with tension, right? And we already used everything in this side. Well, now let's look on the side for mass 2. Here's T again. And we said that this tension is equal to this tension. So maybe we could use this equation, and then let me show you. We do have mass 2. We know what G is. So I'm going to move tension to the right to make it positive, right? I'm going to move tension to the right. And then it looked like this. M2G is equal to tension. Think about it. This mass is not moving. Tension is holding the weight of the mass, of this hanging mass. These two forces are equal in magnitude but opposite in direction. So there you go. Now what I'll do is I'll substitute M2G for this tension, because these two tensions are the same. In fact, let me write it down over here. So tension is also equal to M2G. So now I'm going to set them up equal to each other, right? Because both of them are equal to T. And I'll have mu sub s, coefficient of static friction, times M1 times G is equal to M2 times G. I'm hoping you see that the acceleration due to gravity will cancel. And now we have mu sub s times m1 is equal to m2. So to solve for the coefficient of static friction, that's super simple. We just divide by mass 1. And we have that the coefficient of static friction is equal to mass 2 divided by mass 1. Let's substitute our numbers, and the coefficient of static friction is equal to mass 2, which was 85 grams. Now, in this case, some of you are thinking we have to convert it to kilograms, and I could do that, of course. I don't have to because both my numbers are in grams, so the units will cancel, right? Because if I convert this into kilograms and then convert the 165 into kilograms, in fact, I'm going to do it just to show you. I'm going to get the same number, okay? Now, if it makes you feel better, you can convert it into kilograms. In fact, I encourage for you to do that. In this case, I'm going to do it for sake of time, but I could do. Now, let's say if I were given, if this was in grams and this in kilograms, then I would have to convert 1 to grams or to kilograms, so I have the same unit, either both grams or both kilograms, okay? In this case, I'm going to leave it in grams, so it'll be 85 grams divided by 165 grams. That's how I'll get my coefficient of static friction. Let's use decimals for that real quick. So I have 85 divided by 165. And my coefficient of friction is 0.51, let's say 0.52, right? 0.52. Don't forget, because it's a coefficient, it has no units. This is one of the few things in physics that has no units. So mu sub s equals 0.52. And that is the answer. That and nothing more. That is the coefficient of static friction. What I want to show you is the ratio now in kilograms, right? So I can prove to you that it'd be the same thing. So it'll be 0.085 divided by 0.165. Same number, okay? Just make sure you have either both grams and both kilograms. And that is it, guys. Don't forget to follow the steps that you're given. Of course, analyze the situation. If you don't have a sketch, make sure you draw a sketch. Draw your free body diagrams. If needed, identify what would be the natural motion, so you can find the natural direction of motion, so you can state if your forces are positive or negative when you have two masses. Sum your forces, add the ones on the y, then the ones on the x, then do the same for the second mass. Use relationships and find whatever you need to find. That's it. Bye.